Welcome to Aksharshala. Today we are going to discuss about monostable multivibrator and various types of monostable multivibrator and expression for the gate width capital T of a monostable multivibrator and waveforms of the collector coupled monostable multivibrator we will see in this video. Monostable multivibrator. As the name indicates, mono means one. Monostable multivibrator has got only one permanent stable state. In the other state being quasi-stable state. Under quiescent conditions. Quiescent conditions means as soon as circuit is connected to supply, when it is properly biased, the monostable multivibrator will be in stable state only. A triggering signal is required to induce a transition from the stable state to the quasi-stable state. Once triggered properly, the circuit may remain in its quasi-stable state for a time which is very long compared to the time of transition between the states. And after that, it will return to its original stable state. No external triggering signal is required to induce this reverse transition. Reverse transition means to come back from quasi-stable state to stable state. It doesn't require any external triggering. In a monostable multivibrator, one coupling element is resistor, another coupling element is capacitor. Why? Because it has only one stable state. So here coupling element resistor corresponds to stable state and this coupling element capacitor corresponds to quasi-stable state. When triggered, since the circuit returns to its original state by itself without requiring any external triggering, it comes back to its original state after a time capital T period. For this reason, monostable multivibrator is also known by other names like one shot, a single step, or a uni-vibrator. Since it generates a rectangular waveform, output of monostable multivibrator is a rectangular waveform which can be used to gate other circuits. It is used to drive other circuits. For this reason, it is also called as a gating circuit. Furthermore, it generates a fast transition at a predetermined time capital T after the input trigger. It is also referred to as a delay circuit. Monostable multivibrators are broadly classified into two types: collector coupled monostable multivibrator and second one is emitter coupled monostable multivibrator. This figure is a circuit diagram of collector to base coupled or simply collector coupled monostable multivibrator. Collector coupled monostable multivibrator which is implemented by using NPN transistors. Both are NPN transistors. Q1 and Q2 are NPN transistors. This is the circuit diagram of collector coupled monostable multivibrator implemented using NPN transistors. The collector of Q2, this is the collector of Q2, is coupled to the base of Q1 by a resistor R1, and the collector of Q1, this is the collector of Q1, is coupled to the base of the transistor Q2 by a coupling element capacitor C. Here this C1 is the commutating capacitor. So already I explained the importance of commutating capacitor in last video. So this C1 is the commutating capacitor introduced to increase the speed of operation. The base of Q1 is directly connected to the minus VBB. Here base is connected to the minus VBB. So base of the transistor Q1 is connected to minus VBB. So hence it doesn't get any base drive. Its cut-in potential is less than 0.6 volts. Hence it is driven into cutoff. Q1 is driven into cutoff. It won't conduct. So here the base of the transistor Q1 is connected to minus VBB through resistor R2. Hence it is driven into cutoff. Under quiescent conditions, so once it is connected to supply voltage, immediately transistor Q1 enters into cutoff region to ensure that Q1 is cut off under quiescent conditions. The base of Q2, see, this is the base of Q2 is connected to the VCC through resistor R to ensure Q2 is on under quiescent conditions. In fact, here instead of connecting this R to VCC, you can connect here one arbitrary voltage source which is less than VCC. But what happens? One more voltage source required if you connect this R to another voltage source. So cost increases. Instead of connecting it to another voltage source, connect it to directly VCC, then cost decreases. This is somewhat advantageous to implement monostable multivibrators. So the circuit parameters are selected such that under quiescent conditions, the monostable multivibrator finds itself in its permanent stable state. So once the circuit is properly biased, immediately it will be in permanent stable state with Q2 on and Q1 off. This is the stable state. Suppose if you want to induce a transition into the stable state, it requires external triggering. So this external triggering will be applied at the collector of off transistor or at the base of on transistor. Why? Because even if you apply here, this will be coupled to base of on transistor only. Directly you can apply at the base of the on transistor. Wherever you want, you can apply. Then what happens? If you apply a negative trigger at the base of the transistor Q2, this Q2 enters into cutoff. If Q2 enters into cutoff, what happens? No current flows in the output circuit. Then C2 voltage is equivalent to VCC. Why? Because no drop across RC, no. So entire VCC will appear at C2. This C2 is coupled to the base of the transistor Q1, which makes the transistor Q1 on. Then when Q1 is on, Q2 enters into off. Since triggering signal is applied to only one device and do not to the both the devices simultaneously, unsymmetrical triggering is employed. And unsymmetrical triggering means triggering signal is applied to only one device and the triggering signal is not applied to both the devices simultaneously. That type of triggering is called unsymmetrical triggering. When a negative signal is applied at the base of transistor Q2 at t equivalent to 0, I am applying a negative spike at t equivalent 0. So due to regenerative action, Q2 goes into off, Q1 goes into on state. So due to regenerative action, Q1 will become on, Q2 will become off. Initially Q1 is off, Q2 is on. Upon the application of external triggering, it enters into another state where Q1 is on, Q2 is off. When Q1 is on, now Q1 is on. Then what happens when Q1 is on? When Q1 is on, what happens? See, heavy current flows in the output circuit. I1 flows through RC. And hence, what happens to, so heavy, there will be more drop across RC. Then collector voltage of first transistor is given by VCC minus I1 RC. So voltage at this point, voltage at collector point of first transistor drops. How much it decreases? It decreases by drop across RC. Drop across RC is given by I1 multiplied by RC. So collector potential, collector voltage of transistor Q1 decreases by I1 RC. Initially, when transistor Q1 is in off state, collector potential is equivalent to VCC. When Q1 starts conducting, when it comes into on state, collector potential suddenly decreases by I1 RC. This drop will be, so this decrease in collector potential immediately connected to the base of the another transistor, through the coupling element capacitor C. So at T equivalent to 0 plus, the base voltage of Q2 is how much it decreases? Initially it is VB sat. Now it decreases by how much? I1 RC. So same decrease is coupled to the base of the transistor, no? So now base potential of transistor Q2 also decreases by I1 RC. So initially it is VB sat. Now it decreases, and you have to subtract I1 RC from VB sat. So at T equivalent to 0 plus, the base potential of transistor Q2 is VB sat minus I1 RC. Capital T. So when T equivalent to capital T, reverse original circuit comes back to its original state. At T equivalent to 0, it enters into quasi-stable state, and at T equivalent to capital T, it comes back to its. Let us derive expression for this capital. So here this is the waveform at the base of the transistor Q2, of monostable multivibrator, which is shown in this figure. The base potential is drawn here. Base potential of transistor Q2. The potential at this point is shown here. Initial voltage is VB sat minus I1 RC. So here when Q1 is off, all the applied potential will be appear at collector of transistor Q1. Why? Because no current flows when transistor is off. So VC1 equivalent VCC at T equivalent to 0 minus when Q1 is off. And to capital T. So at this point, at T equivalent to capital T, VB2 equivalent how much? V gamma. Now replace VB2 by V gamma at T equivalent to capital T. So at T equivalent to capital T, VB2 equivalent to V gamma. Therefore V gamma equivalent to VCC minus same expression you can write here. So that equivalent VCC you can bring this expression to left side. 2 VCC minus VB sat plus VC sat into e power minus t by tau equivalent VCC minus V gamma. Now you can write e power minus t by tau as subject. If you write e power capital T by tau, you will get this expression. From the above equation. Now define log on both sides. Capital T by tau equivalent log 2V. Again 2 also taken as common. 2 into VCC minus VC sat plus VB sat by 2 by VCC minus V gamma. Now send this tau to this side and expand log. So T equivalent tau log 2. So here log of AB, log A plus log B. So tau log A means 2, log 2 plus tau log B means this term, all this term. This is log. So tau log VCC minus VC sat plus VB sat by 2 by VCC minus V gamma. Again see this term VC sat plus VB sat by 2. this is the average of junction voltages. Generally for any transistor under quiescent conditions, under normal conditions, we see average of junction voltages is equivalent to cut-in voltage. Cut-in voltage is V gamma. So then this entire term is equivalent to VCC minus V gamma by VCC minus V gamma. Then this will become tau log 1. For any base, log 1 equivalent to 0. So this entire second term will be equivalent to 0. So then gate width capital T equivalent tau log 2 only. So normally for a transistor at room temperature, the cut-in voltage is the average of the saturation junction voltages for either germanium and or silicon transistors. So V gamma equivalent to VC sat plus VB sat by 2. So then what happens? You will get, and second term vanishes, and you will get expression for capital T equivalent to only tau log 2. So what the value of log 2? 0.693. Tau equivalent to R plus R naught into C, where this R naught is the output resistance of transistor Q1. So the output resistance of conducting resistance is very small compared to R. So R plus R naught will be taken as R only. So finally T equivalent 0.6 stable state. Now let us see waveforms of the collector coupled monostable multivibrator. This is the, just now only we have seen, this is the base potential of transistor Q2. This is the collector potential of transistor Q1. And this is the collector potential of transistor Q2, and this is base potential of transistor Q1. So with this, I am closing this video. For any queries, please contact aksharshala@gmail.com. For further updates, please subscribe to Aksharshala. Thank you.